speed of light was first measured. Now, I want you to stop and think about the absolute absurdity of this problem. Look around the room you're sitting in right now. You flip a switch and instantly the room is flooded with light. You look out the window at a tree a mile away and you see the tree exactly as it is the very instant you look at it. For thousands of years, the smartest people on the planet, guys like Aristotle, Descartes, the big name, looked at this exact same phenomenon and concluded that light does not travel at all. They said, look, there is no delay. Light isn't a thing that moves from point A to point B. Light is simply a property of the universe. It is a rigid connection. They thought of it like a stick. If I have a stick that is 1,000,000 miles long and I push my end, your end moves at the exact same time, instantaneous. No speed. But in physics, we don't just accept what our eyes casually tell us. We have to be suspicious. We have to ask if light is not instantaneous, even if it actually takes time to go from the lamp to your eyeball, how would you even know? To measure the speed of anything, you need exactly two things. You need a ruler to measure the distance, and you need a clock to measure the time. You watch a horse run down a track. You know the track is 1 mile long. You start your stopwatch when the horse starts. You stop it when the horse finishes. You divide the distance by the time, and bang, you have the speed. You can do this for a train. You can do it for a sound wave. You see a lightning strike. You wait, you hear the thunder. 3 seconds later, you know sound takes time. But light is the thing you are using to see the horse, the train, and the lightning. You never see the lightning before the lightning illuminates the clouds. So if light actually has a speed, it must be moving so incredibly fast that no ordinary physical clock you can build with gears and springs can tick fast enough to catch it, and no ordinary distance on Earth is long enough to make a measurable difference. The time interval between light leaves a lamp and light hits your eye is so close to zero that you can't measure it, and you cannot divide by zero. So we are stuck. How do you measure something that outruns your ability to measure it? You have to cheat. You have to either find a way to stretch the distance to an astronomical, mind-boggling scale, or you have to invent a clock that ticks not in seconds, not in tenths of a second, but in millions of a second. This lecture is the exact step-by-step mechanical story of how human beings figured out how to do exactly that. No magic, no abstract philosophy, no sugarcoating. Just pure brute force mechanics, gears, mirrors, the moons of Jupiter, and simple unbreakable geometry. I'm going to walk you through how we trapped light, exactly how the instruments were built, what went wrong, and how we got the numbers. Let us start at the beginning. The year is 1638, Galileo Galilei. He is the first guy to say, let's stop arguing philosophy and actually do an experiment. He realizes you need a controlled setup. He proposes something very simple, very logical. You take two guys, let's call them man A and man B. You give each of them a lantern, but not a regular lantern, a lantern with a mechanical wooden shutter over it so you can block the light and then suddenly reveal it. You take these two guys and you put them on two different hilltops near Florence, Italy. Let's say the hills are 1 mile apart. It is dead of night, pitch black. Here is the plan. Man A opens his shutter. The instant the light escapes, it travels 1 mile across the valley to man B. Man B is staring into the dark, the very microsecond. Man B sees the light from man A. He rips open his own shutter. The light from man B travels 1 mile back to man A. Man A has a water clock, a device that drips water at a steady rate into a measuring cup. He starts the clock when he opens the shutter. He stops the clock when he sees the return light. You have the distance, 2 miles total round trip. You have the time, the amount of water in the cup. Divide distance by time, you get the speed of light. Galileo actually tried this. He sent his assistants out to the hills. What happened? Man A opened his shutter, and absolutely instantly, he saw the light from man B. There was a delay, but it was just the physical clumsiness of the guys moving their hands. So Galileo says, okay, the distance is too short. They move the hills further apart, 2 miles apart, 3 miles apart. They do it again. The result is exactly the same. The delay did not increase. Why did this fail? We have to analyze the physical mechanics of the human body. What is actually happening on that hill? Three distinct events are taking place. Event 1, light travels from hill A to hill B. Event 2, the light enters man B's eyeball. It hits his retina. A chemical reaction happens. An electrical signal travels up his optic nerve to his brain. His brain processes the signal. Aha, I see light. His brain sends a new electrical signal down his spinal cord, out to his arm, into his hand muscles. His muscles contract and he pulls the wooden shutter open. Event 3, light travels from hill B back to hill A. Today we know that human biological reaction time, event number 2, takes about 0.2 seconds if you are really paying attention. Do you know how far light can travel in 0.2 seconds? It can travel around the entire equator of the Earth 1.5 times. The actual time it took for the light to cross the 1-mile valley between the two hills was about 0.000005 seconds. Galileo was not measuring the speed of light. He was measuring the speed of his assistant nervous system. The biological noise completely swallowed the physics signal. Galileo looked at his water clock, looked at the data, and concluded exactly what a good scientist should conclude. He wrote, "If the speed of light is not infinite, it is at least extraordinarily swift." He proved that earthly distances are simply too pathetic, too short to catch light with a human hand. This leaves us with a tremendous cliffhanger. If the Earth is too small and our hands are too slow, where do we go? We have to leave the Earth. We have to go to space. We move forward in time to the year 1676. A Danish astronomer named Ole Roma is working at the Royal Observatory in Paris. Now, Roma is not trying to measure the speed of light. Nobody is paying him to do that. He is trying to solve the biggest, most expensive practical problem of the 17th century: navigation at sea. If you're on a ship in the middle of the ocean, finding your latitude, how far north or south you are, is easy. You just measure the angle of the North Star above the horizon. But finding your longitude, how far east or west you are, is a nightmare, because the Earth is spinning. To know your longitude, you need to know exactly what time it is back at your home port, say Paris. If you know it is exactly 12 o'clock noon in Paris, but the sun is directly over your head on the ship, meaning it is local noon, you compare the times, calculate the rotation of the Earth, and you know exactly where you are. But there is a catch. You need a clock to keep Paris time on the ship. In 1676, the only accurate clock's a pendulum clock. Put a pendulum clock on a wooden ship rocking in the Atlantic Ocean, and it becomes completely useless. So astronomers say, don't use a mechanical clock, use the sky. The sky is a giant, perfect clock mechanism made by gravity. They look at Jupiter. Jupiter is huge, and it has moons. The innermost moon of Jupiter is named Io. Io orbits Jupiter incredibly fast. It goes around Jupiter once every 42.5 hours. It is a highly predictable, unbreakable mechanical system, and because Jupiter casts a massive shadow into space every time Io goes around the back of Jupiter, it hits that shadow and completely disappears. An eclipse, then a few hours later it pops out the other side. The idea was brilliant. Roma's boss tells him, watch your Io, time exactly when it goes into the shadow and exactly when it comes out. Do this for years, build a table, a massive schedule of exactly when every eclipse will happen for the next 10 years in Paris time. Then we print a book. We give it to a ship captain. The captain is in the middle of the ocean. He points his telescope at Jupiter. He waits for Io to disappear. He looks at his book. The book says, Io will disappear at exactly 10:14 p.m. Paris time. Boom. The captain now knows it is 10:14 p.m. in Paris. He checks his local time, calculates his longitude, and he doesn't crash into a reef. So Rome goes to work. He sits at his telescope night after night, freezing in the Paris observatory, logging the exact minute and second Io vanishes. But after a few years of data, Roma looks at his logbook and he notices something deeply disturbing. The celestial clock is broken. The eclipses are not happening on schedule. Let's look at the geometry of the solar system. You have the sun in the middle. Earth is orbiting relatively close to the sun. Jupiter is way out there, orbiting much slower. When Earth and Jupiter are on the exact same side of the sun, meaning Earth is as close to Jupiter as it ever gets, Romeo logs the eclipses. They happen exactly 42.5 hours apart. Perfect. But as the months go by, the Earth moves faster in its orbit. Earth starts swinging around the sun, physically moving away from Jupiter. As Earth moves further away, Roma notices that the eclipses of Io start happening late. They are a few seconds late. Then, a week later, they are a minute late. 6 months pass. Earth is now on the exact opposite side of the sun from Jupiter. Earth is now at its absolute maximum possible distance from Jupiter. The distance has increased by exactly the diameter of Earth's orbit. Roma checks the eclipse. It is late. It is a full 22 minutes behind the schedule he calculated. Then, Earth continues its orbit. It starts coming around the other side of the sun, physically moving back toward Jupiter. What happens to the eclipses? They start catching up. They are 15 minutes late, then 10 minutes late, then 5. Another 6 months pass. Earth is back on the same side of the sun, right next to Jupiter again. Roma checks the eclipse. Boom! It is exactly back on schedule, not 1 second late. Now, Roma has to think like a physicist. What is happening? Is Io physically slowing down and speeding up in its orbit? Impossible. Io is a massive rock floating in a frictionless vacuum. Conservation of angular momentum says it cannot change its speed. The physical event, the moon entering the shadow, is happening at perfectly regular intervals. The discrepancy is not in the event. The discrepancy is in the signal carrying the information of the event to Earth. Roma realizes the monumental truth. When Earth is far away, the light reflecting off Io, the visual information that the eclipse has happened, has to travel an extra distance. It has to cross the entire diameter of the Earth's orbit around the sun. The eclipse is 22 minutes late because it literally takes light 22 minutes to cross that massive expanse of empty space. Roma had done it. He found the astronomical distance and he used the Earth's orbit as the clock. Now let's do the arithmetic, because physics is numbers. In 1676, astronomers had a rough estimate of the diameter of Earth's orbit. They thought it was about 276 million kilometers. Roma has the distance, 276 million kilometers. Roma has the time, 22 minutes. Let's convert that to seconds. 22 times 60 is 1,000 is 320 seconds. Speed equals distance divided by time. 276 million divided by 1,320. Roma calculates the speed of light to be roughly 210,000 kilometers per second. Now, let's be totally honest here. The actual, true speed of light as we know it today is 299,792 kilometers per second. Roma's number was off by about 25 to 30%. Why? Did his logic fail? No. His logic was flawless. The error was in the input data. First, the astronomers in the 17th century didn't have radar. Their measurement of the distance from the Earth to the sun was slightly too small. Second, Roma's timing of exactly when Io completely vanished was a bit fuzzy because the Earth's atmosphere boils and distorts telescope images, and Io fades out gradually. It doesn't just instantly click off. We know today that light actually takes about 16.6 minutes to cross Earth's orbit, not 22 minutes. But Roma's exact number does not matter one bit. What matters is the monumental shift in human understanding. He proved with hard, indisputable observational data that light is not instantaneous. Light is a physical thing moving at a finite speed through the vacuum of space. You would think the scientific community threw him a parade. They didn't. Scientists are ruthless skeptics. Many prominent scientists, including the director of his own observatory in Paris, a guy named Cassini, completely rejected Roma's paper. Cassini said, Jupiter's atmosphere is probably causing the delay. Or maybe orbits aren't perfectly circular. There are too many variables in planetary motion to prove something as fundamental as the speed of light. They demanded more. They said, if light takes time to travel, show us another way. Show us independent verification using a completely different physical mechanism. All right, 50 years go by. It is now 1728. An English astronomer named James Bradley is going to accidentally prove Roma right while trying to measure something entirely different. Bradley is obsessed with finding stellar parallax. Let me explain parallax because it is crucial. Hold your thumb up right in front of your nose, close your left eye, and look at your thumb with your right eye. Notice what part of the background wall your thumb is blocking. Now, don't move your thumb. Close your right eye and open your left eye. Your thumb appears to jump horizontally against the wall. Did the thumb move? No. Your point of observation moved. The distance between your two eyes creates a baseline, and changing the observation point shifts the apparent position of the foreground object relative to the background. Bradley wants to scale this up to the size of the solar system. If the Earth is orbiting the Sun, then in January, the Earth is on one side of the solar system. In July, it is on the exact opposite side. That is a baseline of 300 million kilometers. And then if you take a telescope and point it at a relatively nearby star in January, and then look at the exact same star in July, that nearby star should appear to shift its position slightly against the super distant background galaxies. If you can measure that tiny angular shift, you can use high school trigonometry to calculate exactly how far away the star is. So Bradley buys a massive, highly precise telescope, but a telescope on a wooden tripod will warp and shift with the weather. So he takes the telescope tube and literally bolts it to the brick chimney of a house so it absolutely cannot move. He points it straight up at the zenith, aiming at a specific star called Gamma Draconis. For an entire year, Bradley carefully measures the exact position of Gamma Draconis in the eyepiece, and he finds a shift. The star is moving. Over the course of a year, the star traces a tiny, perfect little ellipse in the sky. Bradley is thrilled. He thinks he has found parallax, but then he looks closer at the data. He looks at the timing of the shift and his heart sinks. But the mechanics are entirely wrong. Think about the geometry. If this shift was caused by parallax, the star should be at its maximum extreme left position when the Earth is at its maximum extreme right position in the orbit. The maximum shift should happen at the exact ends of the baseline. But Bradley's star was not doing that. The star was showing its maximum shift when the Earth was exactly in the middle of the baseline, moving parallel to the star at its absolute maximum velocity. This is not parallax. This is something completely different. Bradley is stumped. He walks up and down the River Thames trying to figure out what is wrong with his telescope. The story goes that he is on a sailboat on the river. He looks up at the wind vane on top of the mast. He notices that when the boat turns and speeds up, the wind vane changes direction. The wind itself didn't change direction. The apparent wind changed because of the motion of the boat. Boom. Bradley has an epiphany. He invents the umbrella and the rainstorm analogy. I want you to picture this exactly. Imagine you are standing completely still in a rainstorm. There is no wind. The rain is falling perfectly straight down from the sky. You are holding a tall, narrow pipe straight up in the air. The raindrops fall straight down through the pipe without hitting the side. Now I want you to start running forward as fast as you can, still holding the pipe straight up. What happens? Even though the rain is falling straight down because you are physically moving forward, the side of the pipe is going to slam into the raindrop before the drop can make it out the bottom. From your perspective, running, the rain feels like it is slanting into your face. If you want the rain to fall clean through the pipe while you're running, what do you have to do? You have to tilt the pipe forward into the direction you are running. Bradley realized his telescope was the pipe. The starlight from Gamma Draconis was the rain, and the Earth was him running. The light from the star is falling perfectly straight down onto the Earth. But the Earth is moving through space in its orbit around the sun at a massive velocity, about 30 kilometers every single second. In the tiny fraction of a second that it takes the light to travel from the top lens of the telescope down the tube to the eyepiece at the bottom of the telescope is physically carried sideways by the Earth's motion. If the telescope is pointed straight up, the light entering the top will hit the inside wall of the brass tube before it reaches Bradley's eye. To make the starlight hit the exact center of the eyepiece, Bradley had to tilt the telescope slightly forward into the direction of Earth's motion. As the Earth goes around the sun, the direction of its forward motion changes 360 degrees over the year. So the direction you have to tilt the telescope changes 360 degrees over the year, causing the star to trace a tiny circle or ellipse in the sky. This effect is called stellar aberration. Now, why is this so beautiful? Because it is pure, absolute vector addition. It is a simple right triangle. The vertical side of the triangle is the speed of the falling rain, the speed of light. The horizontal side of the triangle is the speed of the runner, the speed of the Earth in its orbit. The angle of the hypotenuse